We've got a couple tag team briefings here from Ted and Andrew. So, Ted, why don't you go ahead and start out?
So I'm going to talk a little bit about what the new stuff coming out of Ezra, the easy radio astronomy software I keep pushing along here. Um, it's an option at least. We all know you can point an antenna at the sky and record 1420 megahertz energy. And as the Earth rotates once a day, you can usually find two places in the sky with stronger power, shown here as um, these bumps in green. Now I push that button. Okay. Your measurements can get more detailed though. You can also record power over many frequency channels. Here the frequency increases up and the time increases to the right. Out in the galaxy, atomic hydrogen atoms emit energy on one frequency, but because those atoms and the Earth are moving, the Doppler effect changes that frequency up and down. Ezra now allows you to plot that plot in 3D with colored power shown on the vertical z-axis. Many thanks to Alex Pettit for finding this Reiner Graph 3D plotting program. You can repeat that process each time pointing your antenna at a different angle up above the horizon. The power bumps start to paint the location of our Milky Way galaxy across the radio sky. Ezra can interpolate your data to smoothly predict the points between your data. The strongest power is shown here in brighter yellow. And Ezra can now allow you to plot that last plot in 3D with colored power shown on the vertical z-axis. Ezra can plot that same data using galactic coordinates. And Ezra can allow you to plot that last plot in 3D with colored power shown here on the vertical z-axis. Ezra can plot that same data on a fancier Malvide projection where the north and south galactic poles are single points. And again, Ezra can allow you to plot that last plot in 3D with colored power shown on the vertical z-axis. So NASA artists present the galaxy from high above. The galaxy center is in the middle, and the sun is shown below, about 2/3 of the way out from the center. We see the galactic arms spiraling out from the center. With enough data, Ezra can plot those galactic arms arching around the center. I am so bold as to label the galactic arms shown in the data. Here is a yellow line at 85 degrees counterclockwise from the top, over down there on the bottom left. This is the line of 85 degrees galactic longitude. Consider the data along that 85-degree line, but in and out of the screen. In other words, consider the data above and below the galactic plane. The Easy GLON program can plot that data above and below the galactic plane. The galactic plane is this thin horizontal line across the middle of the plot. We can see the atomic hydrogen above and below that galactic plane. It is hard to see, but on the left there seems to be two red blotches and a yellow blob maybe. They're easier to see if we increase the vertical angles on the left. Like this. Here we see an angle magnification of 5 times. Now we can clearly see those two red blobs and one yellow blob. Those are slices or cross sections of the galactic arms. at galactic longitude of 85 degrees. Okay, well, that's one cross section at 85 degrees, but Ezra can do that for many other angles of galactic longitude. This, yeah, okay. Other angles of galactic longitude seen, the sun is at that point on the bottom right. And the Reinhardt 3D program can display those many cross sections from the side. The sun is that point at the bottom right. And here's the same data, but the camera has moved, and now the sun is that point at the top right. And so the Reinhardt Graph 3D can create many plots of the same data, and Clipchamp can combine those plots into a movie. Here it appears we are flying a spacecraft around the sun. Each point represented is in, oh, let's do the repeat. There we go. Each point is represented in 3D space, X, Y, and Z. Each point has a hydrogen density value in color. That is a fourth dimension. And each plot in this animation has a different view in time. That is a fifth dimension. So I claim this animation has 5 dimensions. Yikes. So all of this is described on the Ezra website or in an article of the upcoming famous Sarah Journal. Wow. After all that, any questions?
Yeah, I
Very
have
nice. Very nicely done, Ted.
Thank you,
yeah,
Alex, for all the things you've been doing there. Another question that was in there.
yeah. I was wondering if there is in your in the Ezra stuff on GitHub, if there's a well-populated collection of observation data, because like my map of the galaxy right now has like 3 points on it, so I can't really see much in the graphs. Is there some sample data somewhere I could run through it?
Yeah, there's a whole pile of it. All of this stuff I'm plotting with is actually up on the web. Yikes.
Okay.
Um, it's called Shoes. How do we spell it, Rich? HS, no, let's try SHOOS. And it's
Okay.
described on the Ezra YouTube channel. So
Okay.
if you go to my Ezra page and find my videos,
Uh-huh.
one of those is about shoes, and it tells
Okay.
you how to go fetch it and pull it down. A bunch of data.
Okay. That's very helpful. Thank you.
We want more too. Okay. Thanks very much. Back to Rich.
Okay, great job. And for all you Australian group, we need some Southern Hemisphere hydrogen data. So get to it. Uh, okay, Andrew.
Okay, yeah, thank you very much. I'm so pleased that Ted was able to present his stuff first, because he truly deserves credit for what he's done there. And what I'm going to show next is he was kind enough to help me to be the second person only to do the same process with my data. I can't take any credit for the software. I have sort of, I would say, perhaps smoothed out a little bit of the 3D plotting process, or at least the 3D animation process a little bit. But apart from that, everything is really credit to Ted. I'm going to emphasize that. But this is with my personal data, which has come out of Lichfield Radio Observatory here in the UK. So this data's been collected over about a year, and I'll, if I can remember the share now, I'll pull it up and show you. So Ted calls it 5D processing, and I'm still a bit old-fashioned. I still think of it as, oh, sorry, it's 4D process. I think it was 3D processing, but still, I mean, whatever you call it, it's 3 spatial dimensions. So some pictures, if it will work. Why is it not moving? here we are. So I did an animation, put it together. So the sun is located what is seen on the middle there of the z-axis, and you can see two different galactic arms there spinning around. I mean, the software basically allows you to do 0 to 90 degrees well, and you can see that's the bit that I've concentrated on, and we've got a second arm behind it, and you can see the different density within that arm. I don't have as big a dish as Ted does, so I haven't got quite as much detail. But I'm still very impressed with what I got by an 86 by 86 centimeter ex-military array, which is roughly performs at about the level of a 1 meter dish. So I've taken some individual shots from this, done two slightly different ways. So really just taking some images from different directions, some better than others. Then had a go at just indicating, annotating it a bit to show. So that's sort of the direction of rotation there. This is for anybody that wants to follow. If you haven't used Rhino 3D, this won't be relevant at all. But for anybody using Rhino 3D, it's quite important to set the range correctly in order to get rid of some of the spurious bits that come out. And you can use the range setting to get rid of a lot of the RFI, which is what I did here. This is just some various settings that I used. Nearly done. Just another graphic, an attempt to try and copy a bit of what Ted had done and just show it coming over the top there, and trying to compare with a graphic of the orientation of the galaxy. And this is comparing with a map that I created before, again using Ezra with my data, to give you a comparison. So I think that bigger arm on the inside is going to be what I think is the Sagittarius arm, although might be incorrect with my labeling. And the outer one I'd have put down as being the Perseus arm, but perhaps Alex can correct me on this. So I'm sure I got it wrong. And there we are, just to finish with another bit of my my video there. So thank you very much for watching.
Now, Alex, how long did you have to collect data to make that happen?
How long did it take data? Well, that data is from January to November this year.
So there's a lot of drift scans going on in there.
There's a lot of drift scans going on in there. Yeah,
That's neat.
it's around about sort of 4,000 hours, something like that.
So when you look at your data, does each of the slices in a 3D plot represent like a night or a day of collection of data?
Well, no, because if you look at the number of slices, there's only like 12 or 13 slices. So each of the slices represents a particular elevation.
Right, but so then how long did you stay at that elevation before you move on then, I guess?
Well, my standard data collection time is a week.
Okay.
It improves the signal to noise ratio, as I understand it. Basically, it helps swamp some of the RFI. Basically, I have a big RFI problem in my garden. Interference. I definitely have a big problem with interference in my garden. Really big. But if you collect it over a number of days, you can swamp that effect a bit. Probably a bit of data cleaning would do a better job, but still. I got to say, I mean, just from the start of this process, when I started, those who followed my journey, and I know Alex has been a great help to me as well, so I've got to give a great deal of thanks to him, and like Ted, we've got to also give him a lot of credit for having come up with the whole idea of this 3D plotting in the first place, and giving us a basic idea where to get started on it. But so I started off when I was ill a year ago and had a bit of time, and all I dreamt of doing was being able to detect hydrogen. I didn't really expect to be able to get anything more than just detecting it. And then, having detected hydrogen, along comes Ted and he says, "Oh, why don't you try this new software I've written here? And maybe you can help you with your mapping out the Milky Way arms." And I didn't think it was going to work, but it did. Some Milky Way arms. And then when I was about it, it turned out I could demonstrate the smoking gun for dark matter and weigh the Milky Way when I was about it. So I was absolutely flabbergasted that was possible from backyard, something less than a meter. And to do now what is something that I only ever dreamed of doing, being able to create a three-dimensional animation flying through the arms of the Milky Way, just absolutely bowls me over. When will we ever stop as amateurs getting better and better and doing more and more? I don't know. It's quite incredible.
All right. Great, Andrew. Great work.